Welcome to another beautiful Tuesday afternoon, and we are doing physical sciences yesterday. And today we'll be looking at paper number 2 in the final 2020 NCS grade 12 paper. I want to send a big shout out to Liberty. Thank you so much for sponsoring the show. Also, grade 12s, if you haven't done it yet, please do download the Tenfold education app. It is an app filled with tons and tons of past papers that can actually help you guys prepare and finalize your preparations for the final NCS paper that you'll be writing at the end of this year. Also, if you're wondering what question paper we are doing today, or you'd like to join in the fun, please do send a hi on the WhatsApp number on the screen, and you'll meet our friend Dexter, who just like you wants to learn, and then we shall send you the question paper. If you're looking for another platform where we can actually help you guys prepare for your final NCS papers, please do follow us on our YouTube line. We are Mindset Learn. And yes, you are talking to Tobile Nkosi, and I will be the presenter for today's show. So please, without wasting any more time, let us continue. So in last week's show, we finished at question number 4, and in today's show, we're going to be continuing with question number 5. This is the 2020 final NCS paper that was written last year. So question number 5, it says the reaction of calcium carbonate and access, and then they're telling us that its dilute hydrochloric acid is used to investigate one of the factors. Now remember, when we talk about factors, we talk about things that can either increase or decrease the rate of the reaction. The balanced equation for the reaction is given below. And we can see that, okay, it is balanced, and they've given us the phases in which everything is. It's very important when we're doing rates of reaction to know what phase everything is. The same mass of CaCO3, of calcium carbonate, is used in all the experiments. Now that is very important, and the temperature of the hydrochloric acid in all experiments is 40 degrees Celsius. Remember, temperature does play a role at the rate of the reaction. Now the reaction condition for each experiment are summarized in the table below. The experiments are numbered A, B, C. Now remember, if ever you are required to say which experiment was faster or slower or however, you have to stick with A, B, C. Don't say experiment 1 and so forth. Keep it like this because that's what the examiner is looking for. So I can see that the volume for hydrochloric acid was kept the same. I can see that the concentration of hydrochloric acid was kept the same. However, the state of division for the CaCO3 is what changed. In experiment 1, it was granules. In experiment B, was lumps. And in experiment C, it was then powder. Now remember, from grade 12, we know that when we're talking about the rates of the reaction, the state of division of a molecule and stuff actually does affect the rate of the reaction. If something is a solid and if something is in a powder form, there is a different rate of the reaction. It's all about effective collision per unit time. It must go faster. So for question 5.1, for this investigation, we are told to write the dependent variable. Remember, the dependent variable is the one that does not really need the other one. So the dependent variable in this one will be the reaction rate. The reaction rate. That will be the dependent variable. Then the independent variable, the one that stands by itself, dependent depends on what the other one has. So the reaction rate is dependent on what is the state of division of the CaCO3, and then the independent, it would then be our surface area. It will be our surface area. I also think you can actually write state of division. I don't think we would be penalized for that. And then our question continues. Now they're telling us that the carbon dioxide gas, CO2, and that is what is produced during experiment A, is collected in a gas syringe. The volume of gas collected is measured every 20 seconds, and the results obtained are then shown below. So this is the graph that we're having, and I can see that I've got the volume on my vertical axis, the time on my horizontal axis, and I can see that what is happening with the volume and the different phases of time. See what the question says. So the first question for 5.2, it says, what can be deduced, right? So what can really be seen, just a fancy word, what can be deduced from the graph regarding the rate of the reaction during the time intervals of 20 seconds to 40 seconds. So let's go back. Now, you must be specific. They looked at 20 seconds to 40 seconds, right? Now, what can we see between these ones? I can see that there's a decreasing gradient, which indicates that the rate of the reaction is then decreasing. Remember, it's almost going to be done. Remember, when the line is straight, it's almost reached completion. So between the times of 20 to 40 seconds, we have a decreasing gradient. A decreasing gradient. Remember, the steeper it is, it means that the reaction rate is actually going pretty fast. It's a decreasing gradient, and this indicates the rate of reaction the reaction is decreasing. It's decreasing. And then the second one, it says, what can be deduced from the graph again regarding the rate of the reaction between the times of 60 to 120 seconds? So let's go back. Let's see, what can I see? Between 60 and 120 seconds, and I see that it's actually flat. So the gradient is 0. It's not steep and so forth. So the gradient is 0, which indicates that the rate of reaction is also 0. A flat gradient, remember we have a flat gradient, meaning the gradient is 0. Remember, you have to indicate that the gradient is 0 because you're showing the examiner that the reaction rate has actually stopped. So this indicates that the rate is 0. That is 0. Or you could have also actually said that the reaction has stopped. The reaction has stopped. I mean, we also see this when we talk about Le Chatelier's principle. When the gradient is 0, the reaction is stopped. Reaction stopped. The reactants are used up. The reactants are used up. Remember, if there's no more reactants, we cannot make any more product. Let's go to 5.3. Now it says that we need to calculate the average rate in cubic centimeters, (s to the -1), at which carbon dioxide gas is produced in the experiment. Remember, when they say average rate and they do say calculate, you already think in your head, we need a formula. Calculate the average rate at which carbon dioxide is produced in the experiment. So I can go back to this information right here, and I can see that the volume at which I'm given is 500, and then I'm going to look at the time I'm going to get in this equation here, and I can see that the reaction rate actually started reaching completion at the time of 60 seconds. So let's calculate that. Remember, every time they do say calculate in physics and in chemistry, you need to have a formula. So I'm going to have average rate. So if this is for 3 marks, you're going to get a formula. This is the change in volume over the change in time. Remember, it's final minus initial, so the volume here is 500 minus 0. And then the change in time, final was 60, but initially it started off at 0. Now I'm going to just put this in a calculator exactly as it is. I'm not going to include the zeros. So here I'm going to have 500 all over 60. And then you're just going to press that button there that says change. Remember, 2 decimal places. If the third number is less than 5, then it doesn't affect the number before it. And this will be 8,33. And they have given us the SI unit in which we need to use, which is centimeter, cubic centimeter dot S minus 1. That is the average rate. Formula, correct substitution, and then make sure that you have your SI unit. Number 5.4. It says, how will the volume of the carbon dioxide CO2 gas produced in experiment B compared to that in experiment A? We must choose greater than, smaller than, or equal to. I need to go back here. So let's see. If I'm looking at the carbon dioxide produced in A and B, I can see that the volume is the same, concentration is the same. So that means the amount of carbon dioxide produced will also then be equal to. It will be equal to. Now also remember, if the examiner has said choose from greater than, only stick with that. So this was then equal to, and that was then for 1 mark. And number 5.5, a graph is now drawn for experiment C on the same set of axes. How will the gradient of this graph compare to the gradient of the experiment in A? Right? In number A, I must choose greater than, smaller than, and then equal to. Then it continues to say that I must use the collision theory to fully explain my answer. So let's go see what is happening in experiment C and what is happening in experiment A. Let's see the difference. I see that the volume and the concentration is exactly the same. If I'm focusing at C and on A, at A I've got granules, where at C I've got powder, which means then that it will then be greater than, right? It will be greater than. Powder and granules actually affect the state of division when we talk about the rate of a reaction. So it will definitely be greater than, because powder will then act better. So now they're asking us to use the collision theory. Now remember, the collision theory is what we learn in grade 10. And how I always teach my children, if you're going to talk about the collision theory, you must always have certain points that you talk about. You know, most of the time when you talk about collision theory, we include the kinetic energy, how they gain the energy, how they have more effective collision, correct molecular orientation, and then effective collision per unit time, because that is then what speeds the rate of the reaction. Now they're saying use the collision theory to fully explain this answer. In experiment C, we use powder. In experiment A, we used granules. So now you could say for experiment C, so there was various ways you can answer it, but I'm going to show you what the examiner is looking for. Experiment C. So I'm going to make experiment C the center of attention. So first things first, the surface area, because I could see that the volume and the concentration are the same, but what is different is the surface area or the state of division of the CaCO3, which is CO3 powder, which is powder, is then greater than the CaCO3 granules. That's the first difference that I saw, right? Okay, I could further say more particles exposed. More particles exposed. You could have said correct orientation. I'm trying to write one word in two. So correct orientation. That's what it affects. And now remember, when we talk about powder and granules, the powder, what it then does, it's more effective collision. More effective collisions per unit time. And now remember, if there's more effective collisions per unit time, it increases the rate of the reaction. It increases the rate of the reaction. You could have made experiment A the subject of the formula. And then you talk about the differences in between experiment A and C. So we could have said for experiment A, the surface area, of the CaCO3 granules is smaller. We have less particle orientation because it's granules, less particle orientation. And if there's less particle orientation, there's less effective collision. And remember, for the rate of a reaction, you need to have effective collision. So there will be less effective collisions per unit time. That word is pretty important, per unit time. Now remember, if there's less effective collision per unit time, this then decreases. It decreases the rate of reaction. So you could have said it in any way. So now I see that there's 4 marks. I would have 4 valid points on how to explain it. For experiment C, I focus on it being powder and how powder was then faster than the granules. You must say it in step by step to show the examiner that you know exactly what's going on. Let's look at our last question. Now it's telling us assume the molar mass gas volume at 40. Now they've already given us, gas volume, molar gas volume. That is something that they've introduced actually in grade 11. But molar gas volume at 40 degrees Celsius is 25.7 cubic decimeter per mole to exponent 1. Now we must calculate the mass of the CaCO3 used in experiment 4. So let me see if I can fit it in here. Let me extend this page. There we are. So remember, I'm going to find my mole ratios. I know that they're asking me the molar volume at that. I must calculate the mass of this, right? Now I'm going to use of CO2 because from the experiment given, I am given some information about the CO2 from the equation here below and then so forth. So I'm going to take it from there. But now I need to use mole ratios between the two and then so that I can find my final answer. Just go up a little bit. There we are. So I'm going to use CO2 and I'm going to use CaCO3, right? Because I am looking for the grams of this, but I am given information for CO2. So I'm going to use my mole ratios. So I'm going to say the moles of CO2 is equal to V over my gas volume, which is Vm. And then I know that the volume given is 0.5, right? It's 500 cubic centimeters. I'm going to divide that by 1,000, and then I'm going to get 0.5 because volume must always be in cubic decimeters. So I just did a conversion factor of that. And then I'm going to take the 27 because that is my molar gas volume that is already given to me, which is then 25.7. I'm going to find the moles of my CO2. I'm going to put it exactly as it is in my calculator. So I'm going to have 0.5 and I'm going to have 25.7 because there's no exponents and so forth. I'm not going to put it in brackets. And therefore, I'm going to get 0. So now I'm going to write it to the last 4 decimal places because I'm still going to work with this number. So I'm going to keep it as 0,0195, only because I'm going to need it. Remember, the more you round off your answer, the more it actually moves it further away. Now I'm going to use my mole ratios. The mole of CO2 to the moles of CaCO3. Now, these mole ratios is what you then get from your experiment. So I can see my moles is 1:1. So that means they are therefore equal. It means they are equal. Let me just go all the way down. And we are here. So these moles are equal. So that mole, this means if I found the moles of CO2 as 0,0195, it means that the moles of CaCO3 will also be the same. So then the moles of CaCO3 are also then 0,0195 because this is mole ratios. Remember, we bring in mole ratios in grade 11. I'm never going to say N. Remember, I'm looking for mass is equal to M over big M. But I'm looking for mass. I'm going to make mass the subject of the formula. Put this over 1. I'm going to cross multiply. M times 1 is M. Then I've got N times my molar mass. Now, my moles is 0,0195, and then I must find my big M. Now, my big M is my molar mass for CaCO3 This you find on your periodic table. Calcium will be 40 grams per mole. Carbon will be 12 grams per mole. Plus, I've got 3 oxygens, each with a mass of 16. I would always actually show this where you work it out, because it just helps show the examiner that you know exactly what's going on. 40 plus 12 plus 3 of 16. This is what we learn in grade 10 actually. So it's 100 grams per mole, 100 grams per mole. And this is for calcium carbonate. So my big M, which is my molar mass, is therefore times 100. I'm going to go to my calculator again. So I'm going to say 100 multiplied, just do it from the beginning, 100 multiplied by 0,0195, and therefore I should get my mass, and therefore I get 1,95. I get 1,95. The SI unit for mass is then a small m. That is how we measure mass. The SI unit for mass is a G. The symbol for mass is a small m, but the SI unit is therefore a G. And that is then how I would have answered all these questions. But now remember, if you are still struggling with mole ratios or having to make things equivalent, it is all, most of it, grade 11 concepts. And some of the terminologies like molar volume and all that stuff is concepts from grade 11. If you're having a bit of an issue, I would say take your grade 11 textbook and then just revise on how we would have done it. But nonetheless, that is then how we would have answered question number 5. And then I will check you after the break.
No one ever asks why we do the weird things we do. Like, why once is never enough? Or doing 2 trips is just one too many. Why do we, before we use these? Or say 5, when we mean 20? Why do we have second thoughts? And think that lift buttons make them go faster? Why don't we walk there? Cross our fingers, touch wood, and struggle to hide our true feelings. At Liberty, we want to know all the weird and wonderful things that make us human, because human beings, being human, are what we make financial solutions for. Liberty, in it with you.
Did you know that in 2006 researchers discovered a clam estimated to be 507 years old? In 2006 an ocean clam was discovered off the coast of Iceland, and by counting the growth rings on the shell, scientists estimated its age at an astonishing 507 years old. Born in 1499 during the rule of the Ming dynasty, the clam was nicknamed Ming.
Welcome back from the ad break. You are still sitting with me, Uthobile Nkosi. Welcome to the show, and thank you so much for joining me. And I want to send tons of love to Liberty. Thank you so much for sponsoring the show. A big hug and tons of love coming to you guys from us. And grade 12s, if you haven't done it yet, please do download the Tenfold education app. It is an app filled with tons and tons of past papers that can actually help you prepare for your final NCS question papers. If you are wondering what question paper we are doing, or you'd like to join in the fun, please do send a hi on the WhatsApp number on the screen, and then we shall give you the question paper, or send it to you rather. Also, if you feel like you want another platform where you can check us out, please do check us out on YouTube. We are Mindset Learn. So right before the ad break, we looked at question 5, was a little bit of stoichiometry on the rates of reaction. Now in question number 6, we look at Le Chatelier's principle, more stoichiometry, and all about the KC. So this question goes, the dissociation of iodine molecules to iodine atoms is a reversible reaction. I can actually already see that this is a reversible reaction by looking at this arrow right over here. and it's a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is then given. Now, very important when you're looking at the KC, Le Chatelier, and so forth, looking at your mole ratios, because we know that temperature, pressure, and all those things is very important, and as well as the moles of the balanced equation. We are then further told that the Kc for the reaction at 727 degrees Celsius is 3.76 times 10 to the negative 3. Most of the time they ask us to calculate the Kc. Now that they've given us the Kc already in my mind, I can already see that we're going to have to then work backwards. Now, number 6.1 says, write down the meaning of the term reversible. Now, reversible is not like a jersey that is reversible. In chemistry, it means something completely different. And that this means that products can be converted back to reactants. Products can be converted back to reactants. That is then what reversible means in chemistry. Number 6.2 says, at equilibrium, very, very important. At equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. Now remember that when we then increase or decrease pressure, according to Le Chatelier, the system will shift in such a manner as to counter that stress. Now the following continues to say, how will each of the following be affected? Now remember, the pressure is increased by decreasing volume. So now we must choose only increase, decrease, or remains the same. The first one says the value of the equilibrium constant. So what happens when we increase pressure by decreasing volume, and what happens to the equilibrium constant? It remains the same. It remains the same. Let me go down. Let's look at the other one. Again, at equilibrium, the pressure of the system is increased by decreasing the volume. We must also choose increase, decrease, or remains the same. What will happen to the number of moles of the I2? Now, this one will definitely change. This one will then increase. This will increase. When we increase the pressure by decreasing volume, this one will then increase, meaning that the reverse. Let me just go up, all the way up. It means that this will then increase. Let's go down. So number 6.3 says, explain the answer to question 6.2.2 by referring to Le Chatelier's principle. Now, talking about Le Chatelier's principle, you must talk about the pointers that Le Chatelier says, the same way we used when you talked about the collision theory. Now, this is very crucial because when we increase pressure, now remember, pressure is increased by decreasing the volume. When we increase pressure, the reaction that leads when we increase, let me just check there. Leads to the smaller amount. Leads to the smaller amount of gas molecules. Molecules is favored. And then what this means, therefore, the reverse reaction is favored. So when we increase the pressure, the side with the smaller gas molecules will then be favored. Let me just go up. So let's see, between the two, I can see here I had 2 moles and here I only had 1. So when we increase the pressure by decreasing the volume, the reverse reaction is favored because it has the least gas molecules. It only has one. And that is then the side of the equation that is then favored. Let's look at number 6.4. It says at 227 degrees Celsius, the Kc value for the reverse reaction above is therefore 5.6 times 10 to the negative 12. Is the forward reaction then endothermic or exothermic? And must fully explain our answer. This means therefore if it moves from 3.6 to 5.6, this means then it becomes endothermic. It is an endothermic reaction. Now, endothermic and exothermic reactions is again grade 11. But now the Kc, they say fully explain your answer, and this is for 4 marks. Now let's talk about what actually affects endothermic and exothermic on the Kc. So Kc value decreases with temperature decrease. With temperature decrease. And I can see because now my temperature is 227. Initially, I just want to go all the way up. Initially, my temperature was 727. So I can see that the temperature decreased. So a decrease in temperature will decrease the Kc value will decrease with temperature decrease. And what else happens? We then favor the reverse reaction. The reverse reaction is favored. Reverse reaction is favored. And then a decrease in temperature favors the exothermic. Decrease in temperature favors and let me just say an exothermic reaction. You could have done it the other way around by saying with a temperature increase, here we said with a temperature decrease, we could have said with a temperature increase, the forward reaction is then favored, and then increase in temperature favors the endothermic reaction. So we could have done it like that as well. But we're not going to get penalized for writing it like this. And then here is question number 6.5. So it says a certain mass, we don't know what mass this is, so an unknown mass of iodine molecules, which is I2, I can already see that it has a mole ratio of 1, is sealed in 12.3 cubic decimeter flask at a temperature of 727 degrees Celsius. The Kc, usually we are looking for the Kc, but the Kc is equal to 3.76 times 10 to the negative 3. Now, when equilibrium is reached, the concentration of the iodine atoms is found to be 4.79 times 10 to the negative 3 moles per cubic decimeter, which is concentration, very important. We must calculate the initial mass of the iodine molecules in the flask. Very crucial, you need to first have a balanced equation. I'm going to write it here so I can work half-half on my paper. Remember, our initial reaction equation looked like this. It's 2I and then G. So I had a mole ratio of 2 is to 1. It was a reversible reaction. Now, the nice thing about this question is I'm already given the Kc. Remember, when you're finding the Kc, it's always your products. It's always your products over your reactants. So we also use solid brackets. I'm going to do it the long way around. R. So my products is, I'm going to have I2 here at the top. Remember, the 2 in front becomes an exponent. And then I'm going to have my reactants here at the bottom, which is just a 2. Now, I'm told that the Kc value is 3.76 times 10 to the negative 3. Now, I'm told that the concentration of the iodine atoms, remember for Kc we use concentration, is 4.79, so I'm going to have this one here, 4.79 times 10 to the exponent negative 3. Remember, I do have an exponent 2 outside, and then I'm going to find the value of this I. So this is just mathematics. And I'm going to then cross multiply. I'm going to cross multiply. Let me take this off, and then I'll come back and write on the side so that you can just see what I'm writing. So I'm just going to cross multiply. I'm just going to put a 1 there. I'm going to take that multiplied by 1. I'm going to have 4.79 times 10 to the negative 3 exponent 2 equals, I'm going to have all of this multiplied by the I. I'm going to keep everything in brackets because, I don't know, if you don't keep it in brackets, then the calculator does exponents first. And that is now I2. I'm looking for I2 by itself, so I'm going to divide both sides with what's bothering the I2, which is 3.76 times 10 to the negative 3. What you do on the one side, you have to do on the other side, times 10 to the minus 3. This side and this side will cancel, leaving me with my I2. So I'm going to put it in the calculator exactly as it is. Let me put it on this side. I'm going to put brackets around it. So I'm going to get 4.79 times 10 to the exponent negative 3. Remember, I do have a squared bracket. And at the bottom, I've got 3.76 times 10 to the exponent negative 3. There we are. So there, that's what I get. So I'm going to move my comma. I'm going to move my comma 3 times. So I have the 6. I'm going to say 1, 2, 3. So I'm going to leave it as 6.1021 times 10 to the exponent 3. I've just moved my comma 3 times. Just going to keep it like that. I'm also going to keep it to 3 or 4 decimal places because this is not my final answer. Remember, the more you round off, the more kind of incorrect your answer actually becomes. So that is then what I get for my concentration of my I2. Let me just extend my page a little bit. So therefore, I'm not done. We're still looking for the mass. I haven't even started with the question. I'm going to go back. This was my reaction. Just want to write this down for you, so that when we talk about mole ratios, you know exactly what I'm talking about. This will be 2I and then G. So now I like using the start table. I don't know, your teacher could have taught you how to use either one. I use initial, change, and then equilibrium. Initial, change, equilibrium. I'll just scroll up if I need to. I draw my table like this. I'm going to break it up like that. So now this is for this table respectively, for this one respectively. Now remember, this is the reactant. At the change, the reactants are being used up. But at the change, the products are being formed. Reactants get less while products are being formed. I was told that my I at equilibrium was 4.79 times 10 to the negative 3. Now remember, I just calculated my equilibrium constant for this one, my concentration for my I2, which is here. So I'm going to say 6.1021 times 10 to the negative 3, right? Let me just write mole dm3 to show that that's concentration. Initially, I didn't have any products because remember, when you start a reaction, you've got no products, only reactants, right? So that would be 0. Now 0 plus 4.79 times 10 to the negative 3 will give you 4.79 times 10 to the negative 3. Now we're going to have to use mole ratios. This is how this works. Here I've got 2 moles. So 2 moles is equal to 4.79 times 10 to the exponent 3. I want to find how much was 1 mole. If 2 moles is 4.79 times 10 to the negative 3, I'm going to divide that by 2 so that I can find the value of 1 mole, which will come here. So let's calculate that. I'm going to take my calculator. Let me just move it on the side. So I'm going to take this 4 because they did say at equilibrium, which is 4.79 times 10 to the exponent negative 3. This is 2 moles. I want to find the value of how much was 1 mole. I'm going to divide that by 2 to find the value of 1 mole. So there I found my 1 mole. I'm just going to move my comma again to have it by the point 2. My comma starts there, 1, 2, 3. I'm going to have 2.395 times 10 to the negative 3. I just want to keep it like that. So that will be 2.395 times 10 to the exponent negative 3. Now remember, I don't know what I had initially. I know that I've used up 2.39 times 10 to the negative 3, and at equilibrium, this is what I was left over with. Now, I need to find what I had initially. Now, this is just mathematics. If you've used this, and this is what you've left over, it means the sum of these two is what you've had initially. So I'm just going to add them together so that I can find what I initially had. I'm just going to write it in this manner. 2.395 times 10 to the exponent negative 3. And I'm going to add the 6,01021 times 10 to the exponent negative 3. I do put brackets around it. It just makes it easier. There we are. So I'm just going to move my arrow again so I have it by the 8. 1, 2, 3. So I'm going to leave it as 8.4. 9. So I'm going to leave it as 0,8405. So that's what I had at equilibrium, times 10 to the negative 3. 8, let me just, 8,405, I've got 405 times 10 to the negative 3. So that is what I had at equilibrium. Just want to go over this again. Remember, this is what we had at equilibrium, but this was the value of 2 moles, right? If you have a value of 2 moles, you need to find the value of 1 mole, right? So for me to find 2 moles, I'm going to have to divide this by 2 so that I can find the value of then this one. So that is why I divided it by 2. And then for me to find what I initially have, if this is what I've used up, this is what I had left over, the sum of these two is what gave me this. I'm just going to work on my side so that we can therefore calculate the mass. We are not done yet, right? They did say they want the mass. So now let's move along. I am going to use the formula. I'm going to use the formula. I don't know if I can move there. Now, let me rather move down so that we have enough space. I'm going to use the formula C is equal to M over my big M and then V. I'm going to use this one because I do have the concentration. I'm looking for my mass. I do have my molar mass as well as I do have my volume. Remember they told me it is in a flask which is 12.3 cubic decimeters. So I do have all of that information, and this is the one I am therefore looking for. I'm going to make M the subject of the formula. I'm going to put this over 1, cross multiply. M times 1 will give me M, and then I have my concentration multiplied by all of this, which will be my molar mass, and then my volume. Now remember, my concentration, they said they wanted the initial mass. This is the initial mass that I had, right, before the reaction. So that's then the concentration I will use. Therefore, I got 8,405 times 10 to the negative 3. And then I need to find my big M. Now remember, iodine is 127. So my I2 is equal to 127 on the periodic table. I've got 2 of those. So I just multiply this by 2, and then I'll find my iodine in grams per mole, which is 254. Okay, just did that in my head. Now the volume that I was given was 12.3 cubic decimeters. Now I'm going to find my mass. I'm going to put everything exactly as it is, and then we should get our mass. Remember to put brackets around everything. I'm going to have 8.405 times 10 to the exponent negative 3, right? That is the initial concentration, 254, and I must multiply it by the volume in which the container was, which is 12.3, equal to, and therefore I get 26. Remember the third number will change this one to then a 6. So I'm going to get 26,26. The SI unit for M is then a small g. I think the most important thing that you needed to find out here was this part here by dividing it by 2, and then to remember that they were looking for the initial mass, which you had to find by the initial concentration before equilibrium was reached. Now, it's very important that you actually do practice a lot of Le Chatelier's principles. It is a lot of mathematics, and it's also a lot of mole comparison and stuff, but you'll see once you actually get the hang of it, it's actually pretty easy, but you must make sure that you read your formula or your equation properly and then see everything that you're given. I like using this table, the ICE. Some teachers use the start, some teachers use the in, out, and however, whatever your teacher has used you or taught you to use, stick with that one, but practice as many as you can. They can be a little bit challenging, but they're fairly easy. Okay, that was it for question number 6, and then I'll see you after the break.
Did you know that there is an Asian elephant that can imitate human speech by sticking its trunk into its mouth? An Asian elephant named Koshik has astounded scientists with his Korean language skills. Researchers discovered the mammal has learned to imitate human speech by placing his trunk into his mouth, modulating the shape of his vocal tract. Koshik can say 5 words in Korean: hello, no, sit down, lie down, and good.
Mindsetters, get your grade 12 exam workbooks now. Ask for them at CNA, SPAR, and Pick n Pay stores. You'll find up-to-date CAPS content, past paper downloads, hours and hours of specially paired online video lessons, and so much more. At only 129 Rand, what are you waiting for? Get yours now.
Welcome back to the show, guys. You are still tuned in with me. We are looking at paper number 2 in the year that was written in the year 2020. You are looking and talking to Toby Lenkosi. Thank you so much to Liberty for sponsoring the show. A big shout out and tons of love to you guys. Thank you so much for sponsoring us. I also want to say, grade 12s, if you haven't done it yet, please do download the Tenfold education app. It's an app filled with tons of past papers that can help you prepare for your final exam paper. It also has some memos so you can see where you're actually making mistakes. Also, if you're wondering what question paper we're doing and you'd like to join in the fun, please send a hi to the WhatsApp number on the screen, and then we shall send you the question paper we're doing today. And if you're looking for another platform where you want more help after hours, please do follow us on our YouTube channel. We are Mindset Learn. So the next question we're going to be looking at is question number 7, which is then acids and bases. So the question goes, ethanoic acid, and they've given us the molecular formula, is an ingredient of household vinegar. Now, is ethanoic acid weak or strong acid? And we must therefore give a reason for our answer. Now, it is therefore a weak acid. It is a weak acid because they therefore dissociate, right? Number 7.1.2, an ethanoic acid solution has a pH of 3.85 at 25 degrees Celsius. We must calculate the concentration of the hydronium ions in the solution. Now, you could have done this in various ways. My easiest method to go to, because we are talking about ethanoic acid, I'm just going to use the H3O, where you could have used the pH way, where you say 10, and then you say negative pH as an exponent. For me, that works much more better. I'm going to say 10. The pH is given as 3.85, so that's negative 3.85. And you just put this in your calculator exactly as it is, and then it should give you the correct answer. That's 10 to the exponent negative 3,85. And therefore, this is what I get. So I'm just going to move my comma, 1, 2, 3, 4. So I'm going to get 1,41 times 10 to the negative 4. 1,41 times 10 to the negative 4. And there we are. We found the concentration, and concentration is mole DM3. So let's look at the next one. So we've got sodium ethanoate. There's the molecular formula for it. Forms when ethanoic acid reacts with sodium hydroxide. Now, the first question says to us, will the pH of the sodium ethanoate solution be greater than 7, less than 7, or equal to 7? Now, we know sodium ethanoate will therefore be greater than 7. Greater than. Remember, anything that is greater than 7 means that it forms more into the basic solution, right? It is a base. Now, sodium ethanoate forms when ethanoic acid reacts with sodium hydroxide. Now, the next question says, explain the answer in question 7.1.3 with the aid of a balanced chemical equation. So the examiner wants you to show them that you know when this dissociates or when it's in contact with water, what is then formed or produced. 3COO negative, and remember this will be AQ, plus, now it is in contact with water, which is therefore a liquid, and therefore we will then form CH3, COOH, and OH minus, and I can see this is OH negative, right? Or you could have actually done it in this manner. Or we could have said, if you have CH3, remember I'm taking this from my equation, OONA, this is what I'm using, and then this is also in AQ, which is an aqueous solution, and we put it in water, which is H2O, which is therefore a liquid. Now, this is what will happen. We will then form CH3, COOH, and then NaOH. Right? That's what then will form for this reaction. So there we've used a balanced equation for our answer. Now 7.2 says household vinegar contains 4.52% ethanoic acid by volume. We also have a 1.2 gram impure sample of calcium carbonate is added to 25 cubic centimeters of household vinegar. On completion of the reaction, the excess in ethanoic acid in the household vinegar is neutralized by 14.5 cubic centimeters of a sodium hydroxide solution of concentration 1 mole per cubic decimeter. We've also got a balanced equation here, and I can see all that happened in that reaction. Now, number 7.2.1 says I must calculate the number of moles of the unreacted. How much did not react, the unreacted? So I'm going to use my mole ratios. I'm going to say moles of NaOH. This is what has reacted. I got all of this from the information given. And I'm going to say CV. My concentration was 1 mole per cubic decimeter. And then my volume, I've just converted to 0,0145. And that is my volume. Now, 0,145 times 1 will remain 0,0145. And remember, we were calculating for moles. Now, remember, I'm going to use my mole ratio. So from my equation that I'm given, I can therefore see that my moles and my moles of this and my moles of that is exactly the same. It is a mole ratio of 1:1, which means that my moles of CH3, COOH is exactly the same as my moles of my NaOH, which therefore means that my moles of my CH3COOH is also equal to 0,0145, right? I just took this one, divided it by 1,000 to get it to cubic decimeter. So I just moved my comma. So there I already have my mole ratio now, which is exactly the same. Let's look at the next one. 7.22. So here I'm told that calcium carbonate reacts with ethanoic acid according to the following balanced equation. I must now calculate the percentage calcium carbonate in the impure sample if 1 cubic centimeter of household vinegar has a mass of 1 gram, and this is for 8 marks. So this was a big question, a long one. It was a long question. So one thing that you need to do is make sure that you do balance the equation out, and you actually do see or understand the mole ratios that you are given. What I always say to my children is, what actually works the best, or what I would then do, is actually if you want to draw an actual drawing of what would happen if you're putting this in, or what would happen if you're taking that out, and therefore then you can add, okay, 1 mole of this into this concentration, and therefore then you can actually try and then solve the question. Because questions like this can get a bit confusing if you have to find the percentage of this because this was mixed there and so forth. So that's where most of you guys actually find or get confused. So what I would suggest, if you are going to try and tackle this question, I would say draw everything out that you are given and then convert everything that needs to be converted, and then use your mole ratios to find the moles of the one or the other. Most of the time they give you the most information on the one molecule than on the other. But now we learned from grade 11 that we can use our mole ratios to find the mole of the unknown. Also make sure that everything is actually in the correct SI units. And then therefore you can then calculate or try to solve this certain problem. But nonetheless, guys, I really do hope you did enjoy spending the time with us today in the show. I know Paper 2 is actually a very interesting topic, a lot of mathematics, a lot of stoichiometry, all the way from question 4 actually moving all the way up to question number 8 is a lot of stoichiometry. Another thing that I must actually mention to you guys is that most of your content from grade 12 actually comes from grade 11. So most of the stuff we've done on acids and bases, on mole comparisons and stuff, all comes from grade 11 content. So if you are having a bit of an issue, I would take my grade 11 textbook and then I would sit with it and then make sure that I can actually remember everything that's going on. Another thing that most of you guys actually make is that you rush through the question. You must make sure that is there a comparison between the one thing or the other, especially when you have to calculate the percentage. Make sure that you are actually calculating the percentage of the correct sample. Nonetheless, thank you so much for joining us on the show. Tons of love to Liberty once again. Please do download the Tenfold education app, and then I will see you next time. Biggie, I wasn't gonna finish.